Hi, I'm Justin Gerard, and this is a technical overview of the Decelium protocol, all the major layers with examples. So the target audience for this presentation is someone who's moderately technical and is interested in the kitchen sink presentation. That is, as much content as possible that's summarized in a way to get a broad view of the technology offering. So this presentation, although should be accessible to everyone, I've gone through a lot of work to make that possible. It's primarily probably appropriate for technologists, but I am going to spend time explaining or visualizing some technical concepts in sort of simpler language. So it may be accessible to business people as well, or people that aren't pure computer science grads. The Decelium protocol is software. It's split into three layers. So there's a proof layer, which is all about the computer and security. There's a transfer layer, which is all about communications, and there's a decentralized cloud layer, which is all about orchestration of computers and memory and assets. So you can think of the bottom level being security and identity, the middle layer being communication, and the top layer being virtualization or publishing and all sorts of nice tools that developers like on top. Underneath or within each layer, there are submodules. I'm not going to go through them now because we're about to go through them in detail, but the proof layer has four, the transfer layer has six, and the decentralized cloud layer has six as of today. This is something that as we develop or carve up the modules, sometimes we'll split a module or create a new module or merge modules. So depending on the version of the software, this may or may not look the same. It's probably not going to look the same in 2 years. It doesn't look the same as it did last year, for example. The general realization with the Decelium protocol is that users bring their own computers. And when thinking about internet publishing, when thinking about communications, the key insight is that many corporations, almost all corporations, donate computers for their clients. So the most significant example of this is multiplayer gaming, where corporations take on the job of hosting multiplayer sessions for users, even though the users have almost supercomputers that they're playing with. They still actually are pushing towards a thin client experience, and we see this as a fundamental disadvantage. Actually, sure, you can have some data and logs about player activity, but hosting 40 millisecond ping times for let's say 200,000 players is very expensive. And so our key realization is that, hey, what if it's possible to do work like that on the client side? And that's not just for gaming, it's also for all sorts of data driven applications that have multiplayer or multi user functions or features, sort of like marketplaces, chat apps, video, streaming, things like this. So Decelium is a software that can establish what's called a secure mesh network without AWS or Google Cloud. So what I mean is users bring their devices and they plug into a grid with each other. So each user you can think of as as one of those software layers, as a triangle, and together they build up the logo or a mesh network. So we visualize this generally speaking as one Docker container for every four devices, whether it's a phone or a laptop. That's usually the ratio that we see, is that between 4 and 10 users per miner or Docker container. And that's kind of where our logo came from, that key insight that, hey, if we have one of these servers, let's say for every four users on average, between 4 and 10 users depending on the application, then there's an extremely resilient network that evolves, and this is where the logo came from. When I'm talking about the software, uh, you know, the Decelium code base can run on web browser, PC, Mac, Linux, Docker, and to a limited extent iOS, and definitely Android. Each device runs, again, its own open source software, and as I mentioned, there's three layers. So let's start getting into the layers now. The bottom level layer, and I'm going to go through all three, and by the end of the video, you should have a pretty good overview of what each layer does and what the current capabilities are. The bottom layer is a proof layer. It has a wallet, messaging, encryption, and something called hashes. Let's dive into it. So the example I'm going to go through is encrypting and restoring files. And I'm going to talk about the status quo first for each of these examples. So in the status quo, imagine you have a gigabyte file. It might be a video, something authored, let's say in 2019, and you want to upload that to somewhere for secure storage. So the typical way this works in most applications or web applications is you have to stream this file probably through HTTPS to some sort of secure service, like a web server, probably a Lambda function maybe, or some other function where you can upload chunks of files. And the developer has the responsibility of encrypting and keeping a secure version of this file on a server. So on the right hand side here, we have corporate servers. And out of the corporate servers, eventually what you can do is actually on behalf of the user, you can decrypt the file. And that file can flow to another user or another device. So it's always stored encrypted, and then you have essentially a key management problem. So on your corporate computers or on your business computers, you have this kind of key juggling you have to do, and you have obviously, you have the ability to detect invalid files. So if someone tries to say, hey, I have the same file, you can say, no, you don't, things like that. But all of this work is happening on a server. If you imagine, every user is bringing a 200 megabyte or a gigabyte file, that can be quite expensive quite quickly. Not to mention, you have to worry about privacy and data retention policies, depending on the jurisdiction of usage. So specifically, you can imagine cases like mega upload, or situations where people create services that are open access, but different jurisdictions may or may not enjoy the open access, and quite quickly you have to respond to hackers, audit teams, and government or jurisdictional changes with regards to how your IT services are used. You have to deal with like how to custody keys and all this complexity. So the Decelium sort of framework, or the multi-agent or decentralized, whatever you want to call it, the user device first version of this solution sees users running the Decelium software locally on their own personal computer, deriving their own keys. And then on their own devices, there's standard software that will generate the encrypted file locally. So it can be end-to-end encrypted, and also derive proofs of the file's existence, like little hashes that can be sent around to other users manually as proof of the document. You can even give these outputted files, you can send them to a backup server in plain text. It doesn't even matter if it's securely transferred because they're all encrypted. And what that gives you later is, even if the originator is offline, if someone adds the key to the equation, you can recover the original file, and anyone that has the hashes can prove or spot impersonators or invalid files. So right away, on a fundamental level, the Decelium codebase on the proofs it provides a library that works on the same on a laptop, the same in Python, the same on a mobile phone, the same in a website, the exact same encryption and proof mechanisms. So it's really easy to generate files in whatever language you're in, share proof information. However, all this transfer operations, all these in this example, are done manually. So the pros of this library are, hey, you can get some of these workflows and some of these security workflows done without relying on any corporate assets. You can build them into your mobile apps directly, in your local Android app, in your local, Windows or Unity 3D app, in your local Python application or Docker container. You don't even have to touch corporate resources or have any jurisdictional challenges, right? That's essentially the benefit there. So the proof layer is interesting by itself, but obviously doesn't provide a lot of utility. If you want to make a chat application, you're in a situation where you have to sit on top of the messaging module, sending bytes or packages back and forth between other nodes. So it's not different than just any other cryptography library. Things start to get somewhat interesting with the transfer layer. So the proof layer has to exist. The transfer layer is where some of the, you could say, Decelium-like features start to emerge, which allow individuals or individual applications to take on workloads and do interesting work. So in the transfer layer, we have the ability to upload files and actually web apps, to host websites, to manage users, to manage versions of files, to propagate information through the network according to a policy, and to actually register your own computer as a service provider or update your registration of foreign service providers. So you can actually publish endpoints into the Decelium network, and anywhere in the world someone can pull down that service and access your whatever you're offering. It might be like an address service or a map service. You can just connect into the network and provide that service. So for the transfer example, I'm going to talk about a very foundational web journey, which is I'm a developer and I want to upload a website and then I want someone else to visit it. So this is a fun example because it was a difficult challenge for the Decelium network some years ago, but since then has become sort of a meat and potato sort of like hello world example of what the platform can do. And so first we'll talk about the status quo. So the status quo in general is a developer on their developer computer creates an application and it's a website and they want people to visit it. So they'll go and they'll register for something like AWS or Google Cloud, or they'll do this on behalf of a client and they will upload their application. And if they want to be very serverless, the most serverless as possible. So, this is giving, this is the easiest way to deploy a website in 2024. You have a static website, you just ram it into a Lambda or put it up on Vercel or something. So you put your application there. You then have to update your DNS records on somewhere like GoDaddy or Squarespace, whatever you use to point to your web server. I'm skipping, anyway, API gateway details. But in general, you connect your DNS to some sort of Lambda or serverless function. This is the simplest way to deploy an app. And then you're done. And users can visit your website. So it's hard to get simpler than this, right? Like this is a pretty simple workflow. The problem is when you actually come to manage these services. So of course, you have to worry about attackers targeting your Lambda, trying to find weaknesses. You have to worry about denial of service attacks where many computers try to attack your service at once. And there's two outcomes here, either or three. One, you catch a denial of service attack and deny service. That's problem number one, because maybe good users get blocked out. Maybe not though. Problem number two is that, if you don't lock people out, then you deal with exorbitant usage fees. And this is where you get economic attacks on people who publish apps, where you just run a bot to charge up somebody's AWS bill in your spare time for fun. And this can happen, and does happen. And third is people trying to attack the actual corporate account. And fourth, obviously, depending on the nature of your app and different jurisdictions, you might have to, because you're officially a custodian of this app, you run it, you operate it. It's not just a tool you've given to somebody. It's not a refrigerator. Because you custody the operations of the app, you have legal responsibilities to treat data, to warn users of, you have to meet certain privacy standards. You have to have cookie rules, all kinds of work you have to do to create a compliant website in 2024. So that's a lot of extra work. So yeah, easy to launch for sure, but this custodial challenge raises the bar of the difficulty challenge quite a bit. The Decelium process is a bit different. So as we mentioned in the past, or I've mentioned in the past, it doesn't change the application development at all. It's the same application, but where you deploy it is different. So instead of deploying on corporate servers, with the transfer layer, what you do is actually deploy the app using the upload function, or the upload module, I should say, to one of just some person in your mesh network that's registered as being part of the application. And what happens is the propagator actually spreads that application around the user base. So that application is actually self-hosted on your user's computer. So if you imagine you have banking software, then the users are running some of the banking application themselves, the server side portion themselves. So once the app is spread, or even if it's, the minimum is one or two people have it just for redundancy. Once a couple people have a copy of this app, then users can actually visit the app. And how that works is, hey, they still have to hit GoDaddy, they still have to hit Squarespace to resolve the DNS. But as soon as the DNS is resolved, they end up getting redirected to one of the users on your network. So you probably have some special users or special IP addresses registered that can route the request into the network. And after that, the Decelium layer can handle WebRTC or NAT punch through and actually can reach a larger amount of the network. But, essentially they get redirected into the network, and then they can, any one of the computers on the network can host the app. So as you can see, other than the DNS service pointing to a user, it's users operating the app. That actually simplifies a lot of problems when it comes to dealing with denial of service attacks, because that means someone trying to deny service, they will effectively have to attack your whole user base, which is practically impossible, especially when people are behind routers or don't have public IP addresses. It's I don't want to say you can never say it's impossible to hack something, but hacking a user base compared to hacking someone's one or two servers or 10 servers is, you know, could be if it's even if it's a medium successful, even if it's a an app that only has 500 users, it's, it might be 50 times harder. If you're talking about 10,000 or, 20,000 users, it's practically impossible to hack this app, right? In terms of denial of service. That's basically it. So the Decelium layer automatically resolves the versions and synchronizes which version is valid on the network and provides that exact website, and they act as a web host for each other. So other features in the transfer layer include, support for chats, events, image hosting. So, video hosting, contact, email servers can be packaged up in Docker containers and run, payment processing, identity verification, many other sub features. So that is the transfer layer. Forgive this visual anomaly here. I've been meaning to take that out. Yeah, so, version control is part of it. Propagation of application versions and contents part of it. Registration network, user management, hosting, and upload. This is still a pretty low level library. What I mean is, if one is going to use the transfer layer, first of all, it's a paradigm shift to think differently, to not think about throwing everything on AWS, and to architecture applications so it runs client side can take some developer training. So that's one challenge. And another challenge is that the transfer layer alone doesn't deal with discovery or orchestration of the whole network, meaning one using a transfer layer has to, code in your JavaScript or your Node.js or your Angular or whatever your app is, whatever your language is. You have to actually record your user IP addresses and WebRTC contact details, and you have to come up with a system to synchronize those details yourself. So the transfer layer handles transferring, but you still actually have to handle the list of all the authorized users yourself, which for some small apps is not a big, if you're doing a chat app, the transfer layer is fine. It's not a big deal. You have one feature. But if you're making something like a content management system that's decentralized and has lots of records being updated, it can actually become the largest problem to coordinate the intermediate layer. If you're doing a multiplayer game, right, these problems can become harder to solve. And that's actually why the Decelium cloud layer exists. The decentralized cloud layer is in progress now. It's about 1/3 complete. I can actually talk about what's done and what's not done. So right now we're working on containers. We just finished working on storage. We have functions finished, processes finished, memory finished, and search is functional for some searches, but not for complete indexing of all the data that exists on Decelium or can exist. So I'll go through in a second what each of these are. So memory you can think of, if you're familiar with Redis, it's cloud memory, except that it exists on the front end of your app. It means you can put something in storage really quickly, like the last time somebody visited a site and their character level or their chat history, and you can log on a computer, a completely different computer on a different day, and the user types in their identifying information and their chat. All of a sudden, their most recent conversation history pops up very, very quickly. This is good for peer-to-peer applications. It's almost as fast as it's almost good enough for video, but not quite. It would be suitable for multiplayer gaming around 150 milliseconds delay. And it's, again, front-end memory. There's no servers involved. Functions are just like Lambda functions. You upload a piece, right now it's Python, you upload a piece of Python code, and you can invoke that code anytime from anywhere. It will process data for you and send back the response. Processes are what you think they might be. They're programs that run for some time, completing jobs and storing the results. Storage is something that we're working on perfecting now. You can store data in the Decelium network, and what that does under the hood is find an empty computer that's being donated by the community. We have a tokenomic strategy for this eventually, but for now we're just using donated storage space, and where we'll park your data and replicate it up to sorry, with a minimum of 5 copies. And if the copies drop, you could actually call this function and it will find more places to replicate it. In the future, we want to do something similar to what Filecoin does, where you can pin the data and it stays permanently. But for now, it's just, you could think of it as storage that is ubiquitous, that just sits there. Containers is Docker containers, very hard problem, but very fun. Actually being able to have a container that runs for around 5 or 10 minutes at a time and then gets cleaned up and then reboots and runs again. So you can think of it as a forever running container that can do anything from be an email server to a game server for a multiplayer game to anything. And you can control cloud provision, just like it was AWS. And then search and indexing is obviously a very hard problem in decentralized networks, but we do have a search API. So you could, just like on Google Drive, you can search for data on the network that is unencrypted, or your own data that is encrypted that you have the key to decrypt. And you could actually search for strings and user IDs and things like that, and get back a list of records. So these are important functions. And again, they're decentralized over the network. So you just like you're querying something on Ethereum, you just write your query and whatever functions or data or memory pops up. It's ubiquitous across anything connected to the network. So to go over a quick example of this, I wanted to talk about an example that highlights both the strengths and differences inherent in a decentralized system. So we're going to talk about payment servers, something like a t-shirt store. So first, as usual, let's talk about the status quo first. The status quo would involve something like this, where a web application provides a payment screen, maybe a way for someone to buy a t-shirt. There would be a secure backend payment app. So this might be like a JavaScript website, JavaScript HTML. The payment app might be a Next.js or Node.js or Python application that actually has some secrets in it to deal with perhaps the Stripe API, right? And so this is a pretty classic setup for a payment server. When a user submits a payment request, they're going to take some identifying information that is important for their payment that may or may not be secret. It might be public information that they generate, i.e. the Stripe API will give you a payment code, or it could be literally their Visa card information. It depends on the application and the library. But they're going to send this payment JSON to the server. It works its way through and ends up on the Stripe API. This is one way to do it. I don't want to go through the 25 different ways of doing payment forms right now. Obviously, although this can be secured, this is a major attack vector. You're dealing with currency. Depending on what kind of money transfers that are taking place and what's being bought and what's being sold, you might be found to be like a financial entity. You might be found to be responsible for the use of whatever product people are buying. There's a lot of actually, government legislation that can go into offering a paid service online, depending on what it is. So this opens up not just, financial and technical risk just due to being attacked and keys being stolen, but you also have to worry about just like litigation and scaling challenges. Server fees can be for payment apps not too much of an issue, but yeah, there's a lot of vulnerability here. So the same example on Decelium looks very different. First of all, I'm not going to cover the web app example again, but assuming the developer launched a web app onto the Decelium network, you have a few copies lying around. So you're in this familiar situation. Then what happens is on a trusted device, usually a phone. I think people use phones a lot for this. I approve of that because they're always handy. They'll have a very, very, very thin payments app that'll have maybe a private key. And you might actually, what I recommend people do for payments is you have, 3 trusted staff have phones that are always connected to the internet with 3 different payment keys. So you always know, you can always have granular control over the payment mechanism. And they process payments. That's all they do. And so there's, this might be, typically it's something like a 15 to 35 line of code file. And so where's the rest of your payment app, right? You might be asking, like, well, that's not enough to be the whole payment app. And what happens is on the client side, you put most of the payment logic in the client side of the application that they run on their personal computer. And you split the payment description and the payment secrets up. And what happens is the payment secret goes straight to the trusted user device. This is going to be the one part of your application that's very locked down. And this is because this is like a Web 2 gateway. So this is trusted user basically runs your Web 3 to Web 2 gateway. We don't have consensus technology for Stripe API keys yet. So unfortunately, there has to be a place where there is a custodian over this information, but the rest of the application can run in a more Web 3 centric way. The payment description makes it into the trusted users um, script as well. And at this point, what happens is a payment proof will, in the case of Stripe, will emerge from the protocol, usually just like a settlement ID. And that can be packaged up with the payment description inside the web app. And at that point, what happens is this becomes payment history or a ledger entry. Well, the propagator is really great at propagating this payment history. So the network now has history, secure history of this transaction taking place. Whether or not there's user personal identifying information attached, that's up to the application designer. Most importantly, though, the user who actually bought the service or paid has permanent record of their history. Uh, I didn't want to cloud a diagram, but it's also traditional in this case to derive proofs and have proofs baked into some permanent record or permanent storage. So this is an example of how you can take typically a solution which seems, you have to be completely centralized for a solution, and you could reduce the centralized part or the insecure part down to something that fits in somebody's pocket, right? Yeah, that's essentially it. So that's the decentralized cloud portion of the Decelium protocol. I've covered a lot of information, but this should give anyone who's technical a reasonable understanding of what the Decelium protocol is, the kinds of problems it can tackle today, and we are actively working on the cloud layer, and it gives you an idea of where we're going in the next 12 to 24 months as well. The transfer layer and the proof layer are very fully featured and have been used in millions of transactions and tens of products. The decentralized cloud layer has been used a few times, mostly the functions, mostly the memory, and we're still in the alpha stage of the decentralized cloud layer. Thanks very much, and I'll talk to you later.